Back, and today let's solve Leetcode problem 2415 titled Reverse Odd Levels of Binary Tree. So we're given the root of a perfect binary tree and we need to reverse the node values at each odd level of the tree. So for example, suppose the node values at level 3 are this given array of node values 2, 1, 3, 4, 7, 11, 29, and 18. And keep in mind, this is for the node values at level 3. Level 3 is, of course, an odd level, and that's why we have to actually reverse the node values at this level. And if we reverse all of the node values, we simply get 18, 29, 11, 7, 4, 3, 1, 2. We're literally just reversing the order of all the node values in that specific level, if and only if it's odd, like level 3. And then finally, we simply have to return the root of the reversed tree, basically just the final result. So a binary tree is perfect if all parent nodes have 2 children and all leaves are on the same level. And the level of a node is the number of edges along the path between it and the root node. So not really too related to the current problem, but kind of just telling us that basically just defining what a perfect binary tree is, because it does say that we're actually given the root of a perfect binary tree. And for any of you guys who don't know the definition of that vocabulary, they actually give us that right here. Basically, all the parent nodes are going to have exactly 2 children, and all the leaves are going to be on the same level. And what we mean by leaf nodes are basically the nodes at the bottom level or at the end of this binary tree. As you can see, all the ending bottom nodes in this binary tree are actually on the same level, on this last level here. And so this is actually a perfect binary tree, because note that every single parent node, every single node does actually also have 2 children, of course, except of course for all the nodes in all the leaf nodes in the last level. So with that out of the way, let's go ahead and dive straight into the examples here. So for example 1, as you can see, they also give us images to better visualize this. We have this binary tree here, and notice how this tree only has one odd level. That odd level is of course going to be level 1, right? Which is basically just, in this case, the middle level. And level 1 is, of course, odd because 1 is odd, right? And in this case, the nodes at this level 1 are going to be this 3 and this 5, respectively, in that order. And if we reversed all the different node values in this level that are first originally 3, 5, then reversing that, we'd get 5, 3. And so this node would then be 5, and this node would then be 3. And so then we just simply output that resulting binary tree, right? And as you can see in the explanation, again, the tree only has one odd level, and the nodes in this level that are odd, basically level 1, are going to be 3 and 5, and reversing that, we get 5, 3, and then we replace the corresponding nodes with those reversed attributes. So in example 2, we also have another perfect binary tree here. We have 7, and then its 2 left and right nodes are 13 and 11 respectively, also the leaf nodes. And in this case, we're going to reverse the bottom level, because this bottom level is still going to be level 1, right? It's the first level because, of course, this is the 0th level, right? This is the root. And so if we reverse 13 and 11, the 2 node values in this odd level 1, we get 11 and 13. Right? Pretty straightforward here. We're just rearranging, or rather more specifically, reversing the order of these node values in this specific odd level. In this case, level 1 is actually the only odd level. In fact, not just for example 2, but also for example 3 as well. Okay? And finally, for example 3, we don't have an image here, so it's a little bit hard to visualize, but we have this a little bit bigger input here of our binary tree. And in this case, this is our output. Basically, just a good thing to take away from this example is that all of the odd levels actually have non-zero values, right? And the nodes at level 1 were going to be 1, 2, and that after reversing the values at that odd level, at level 1, we get 2, 1, and the nodes at the next odd level were level 3, right? We only had 2 odd levels in this input. That was level 1 and level 3, and after reversing all the nodes in level 3, that odd level, we get 2, 2, 2, 2, 1, 1, 1, 1, and that's going to be after the reversal, and we return hence that resulting binary tree after reversing all of the nodes and their corresponding values in all of the odd value levels. So with those examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to actually solve this problem efficiently, we're going to be using the breadth first search, or the BFS algorithm, right? And we're actually going to use this to traverse our tree level by level, right? As you can see, we literally want to get the odd levels, and so approaching or iterating or traversing over this input binary tree level by level would definitely be quite helpful, right? And effectively, by keeping track of the current level, we can very easily identify odd levels and simply reverse all of the node values in that level accordingly, right? So essentially, for a quick high-level rundown of how our algorithm is actually going to be structured here, first of all, we're going to initially initialize a queue, right? And we're basically going to be using this queue to say basically facilitate level order traversal, right? And what that basically does is it actually allows us to process all the nodes at the current level before we actually move on to the next iteration, or basically the next level for the next iteration. And also, we obviously have to track the current level, and we can do this by simply maintaining a variable to keep track of the current level number, basically monitoring if it's odd or even at that current iteration. And of course, we're going to start from the 0th level, or the 0th value, representing that root level, right? And effectively, while we actually are doing these operations, we have to actually process each level. So first of all, the first basically conditional that we have to have at each iteration of this BFS is to first check, is the level that we're currently iterating over, well, is it actually odd? So if the current level that we're actually iterating over, if it's odd, we then have to actually collect all of the nodes' values, then we have to reverse them, and then we have to also assign them back to the nodes, okay? And finally, we're going to be unqueuing the child nodes, and basically what that means is for each node at the current level, if it's odd, rather not even if it's odd, but for that current level, we have to basically unqueue its left and right nodes, and basically what that means is its left and right children to be able to actually process them in the next iteration. And effectively, we're going to be repeating these operations until we actually process all of the levels of the tree. So with that kind of, sorry about that lengthy explanation out of the way, let's go ahead and dive straight into the code here. So first of all, I'm actually going to be first getting the heap data structure from the heap queue module, or rather the collections module in Python, sorry about that, in this editor here. So from collections, import the DQ data structure. This really isn't necessary for Leetcode, but I just like to do this for best practice. And what this DQ data structure really is, it basically stands for, or rather is an alias for, the double-ended queue, and that basically just allows efficient appending and popping from both ends, hence the name double-ended queue of this data structure. And that's actually very useful and a pretty common data structure for BFS traversals as well. We can pop and append values both to the end and the starting of this data structure in constant time. Very efficient. That's another reason why I'd highly recommend learning how and where you can actually use this data structure. So now let's actually first have a quick base case here. So the base case that we're going to have is if the root is basically none. So if not root, if we have basically kind of like a none input, well then we just immediately want to return none. This is just a quick nice little base case to have to avoid any extra computations. Again, if the root is none, that means the tree is empty and we can immediately return none. We literally have an empty tree. We don't have any nodes or node values, hence. Okay, now let's actually initialize our queue. So I'm literally just going to call it queue and set it equal to a double-ended queue, so a DQ in Python, and we're going to let it start with one value of the root value, right? And we're basically, again, initializing this double-ended queue named queue, and we're first initializing it by adding the root node to it, right? And basically what this queue is going to do is actually help us perform the level order traversal. So now let's actually initialize our level. So level is going to be equal to 0. This is simply going to represent the current level of the tree that we're processing at each iteration of our BFS algorithm. Okay, so now we have the main while loop here for most BFS and even DFS algorithms here while our queue is non-empty, as we actually process each level. So while the queue still has potential nodes to process in it, while it's actually non-empty, so basically while there's still nodes in the queue to actually process each level of the queue, we want to pop off the level size, so the current level size, to be the length of the queue. And basically, we're determining the number of the nodes at the current level by simply getting the length of the queue at this iteration. Okay, oops, sorry about that. Basically, getting the length of the queue at this iteration, and we're just simply storing that in this integer variable level size. Okay, that's great. Now that we've actually initialized this level size, well, now we have to actually use this to check, well, are we actually at an even or odd level? And we can actually use that, or check that, using our level integer. So if the current level number, I should say, if it's actually an odd number, so if we mod it by 2 and get 1, well, that means that the current level is odd. That means when we get the remainder of it when dividing by 0, we don't have a 0 remainder, we have a 1 remainder. And the only numbers that give you a remainder of 1 when dividing by 0 using this modulus operator here are going to be odd numbers. So if this is the case here on line 16, that means we have an odd level. And if that's the case, well, then we know that the level is odd, and we have to actually apply or reverse all of its node values in this given level, like the problem says. So if that's the case, now let's actually start looking at the nodes values to actually start iterating, or rather, reversing them. So I'm going to actually initialize a values to be an empty list here, right? And this is actually going to simply store the values of the nodes at this current odd level in this current iteration, right? And now let's actually loop through the level size. So for I in the, that we defined up here, by the way, on line 15. So for I in the range of simply just the level size here, for I in the range of the level size, we want to get our current node to be the queue at this index I in the range of the current level's size, and then append to our values array in this current level's node at this iteration the actual node's value. So what are we actually doing here in this for loop here? Well, basically, we're just iterating over, using this for loop, all of the nodes in this current level that we stored the level size of in this level size variable. And for each node, we're simply just accessing it by its index from the queue, index I, and then appending its corresponding node value to our values list. Okay, and once we've actually done that, we simply have to reverse our values. So in Python, it's pretty straightforward here. We simply just call values.reverse, simply just reversing all of the values in this list to actually prepare for assigning these reversed values back into the nodes. So now that we've actually reversed the values in this current level of all the different nodes, now we have to actually assign them back to the current levels nodes. So again, for I in the range of the level size, we want to set Q at this index I's value, so Q at I.val, to be equal to values at I. And this is really where that reversed assignment comes into play. Effectively, we're just iterating over the nodes again, and then assigning each of the reversed values back to that current node's values attributes in this kind of reversed form here. Okay, so now that we've actually assigned that, well, what if the level modded by 2 isn't even equal to 1, right? Well, if that's the case, well, then we simply have to just process each node at the current level by removing it from the left of the end, or rather removing it from the left end, sorry, and then appending it to the queue, or rather popping it off from the queue. So in the range, I'm just going to use an underscore here for my placeholder of the level size again. We simply want to set node to be equal to q dot pop left. And this is where that dot pop left really helps us for double-ended queues here for DFS traversals in as a data structure, right? And again, we're simply just processing each node at the current level by just removing it from the left end of the queue using that pop left method and storing it in this node, right? So in this iteration here, well, if node does actually have a left child, well, then we want to add it. So we want to set q dot append node dot left And then we also want to append to the queue the right child as well. So node.right. Okay, and effectively pretty straightforward here. What we're really doing here is simply, if the current node actually does have a left child, well then we want to append both its left and right children to the queue for the next iteration. But you may be wondering, well, okay, we check if it has a left child, and we're adding accordingly if it does, the left child, but why are we also adding the right child to it? Just because it has a left child, just because its left child is not null. It actually exists. Well, if we actually scroll back to the problem statement here, we'll see that we're given the root of a perfect binary tree. And notice how it says a binary tree is perfect if all of the parent nodes have 2 children. And so we're guaranteed that if the current node actually has a left child, it has to have a right child. It can't only have one child. If it has a left, it has to have a right, and interchangeably, if it has a right, it also has to have a left. Either it has both children, or it's a leaf node and it doesn't have any children at all. And that's basically another important attribute of a perfect binary tree. And once we've actually done this, then after we've actually added the left and right nodes to the queue, we want to increment our level by 1. Right? We're simply just incrementing our level variable by 1 to move to the next level of the tree. Okay? And now, once we're actually done with all of these computations here, all of these operations, we simply just have to return the result. And I'm not 100% sure if I indented this correctly, so let me actually just zoom out to make sure it's not unindented on the same level. So return result. It should be right. Awesome. Should be okay. And let me just go ahead and submit this. But before that, I just realized I made a quick error here. The error that I made is that I didn't actually increment my level correctly. I actually have to increment my level outside of this for loop here. So let me just go like that. And now this should be right. Let me just indent this outside right here. Sorry about that, guys. And this should be root, not result. And now this should work. Hopefully it works. Let's just go ahead and check if it works. And as you can see, this is just about as efficient as you can get. Let me just resubmit this for a potential better runtime here. And as you can see, this is just about as efficient as you can get with a 27 millisecond runtime and a 23 megabyte usage for memory. So, for a quick high-level rundown of how this code actually works, effectively, we're actually just traversing this binary tree using this queue, or this double-ended queue rather, that we initialize here. And for each odd level, and we can check that using our level integer variable, we simply have to collect the node values, then reverse them, and then just reassign those reversed values back to the nodes for that current level. And this traversal always ensures that all of the levels are processed and that the modifications are limited only to odd levels. Basically, we check that and ensure that on line 16 by making sure that the level, if it's actually odd or not, by actually taking the modulus of it of 2 and checking if it's equal to 1. And once we're actually done with all these computations for each level in our binary tree, or rather perfect binary tree, we simply have to return the updated binary tree's root. And as you can see, that is really just it. So for the time complexity, this is going to be a big O of n solution, right? And the reason why is because obviously we're going to visit each node exactly once for each parent-child's left and right children. And so, the time complexity is going to be big O of n, and n is going to be the total number of nodes in the tree. Okay, and of course, reversing the nodes, or rather reversing the node values at all the odd levels, is still going to be a big O of k operations for all k nodes at that level. But even then, the overall time complexity is going to remain big O of n fully simplified, because the sum across all of these levels is still going to be a big O of n operation. And for the space complexity, this is going to be a big O of W operation, not really too common. And the reason why is because, let me actually define what W is. The reason why this is a big O of W, W is going to be the maximum width of the binary tree. And the reason why is because for a perfect binary tree, like we saw in the explanation, the width is actually going to be proportional to the number of nodes at that last level, because again, every single child is going to have, or rather every single parent is going to have exactly 2 left and right children nodes, unless of course it's a leaf node, right? And of course, again, the width is hence going to be proportional to the number of nodes at that last level, and that's approximately going to be n half, or n divided by 2, and so the space complexity is also going to be fully simplified, big O of n, removing all coefficients. So that's going to be it for today's video. If you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.